and today we'll be talking about BPMN for VC. And as the title say, it's an extension for the BPMN language, which is adopted by many to model business processes. And the extension itself helps users to integrate blockchain aspects into their business processes. So in this presentation, we will just talk briefly about blockchain-based business processes and what they are. We will move on to the language extension itself, and we will talk about the evaluation and also future work. Okay, so starting with the blockchain-based business process, and so this is the foundation block of the entire work. And what these processes are, what differentiate them than the standard processes is that these processes are executed on the blockchain. So we have a business process that could be presented in different ways. So it could be informal or formal. And just like we will see later, we have the BPMN language, which can describe these processes, and then these processes are compiled or mapped to executable code that can run on the blockchain. Now, in our case, we will talk about mostly Ethereum, and so we'll talk about Solidity code. Once this code is deployed on the blockchain, the code itself, which represents the process, becomes immutable, and none of the participants can actually modify it or tamper with. And eventually, as the process executes, we have also the event log that comes out of the process is also immutable. So whatever happens with the blockchain cannot be changed or modified anymore. So we have a transparent execution log of the process. So the first part of the extension is BPMN, and this is a business process model annotation. It's a standard language for describing business processes. And so one of the features of this language is it also allows us to model inter-organizational business processes, which include multiple participants who wish to collaborate together to achieve their business goals. And in this setting, we suppose not to have a central party. So just a basic overview of the elements of this language. We have the flow objects, we have events, we have activities. Activities are supposed to be executed by the participants, while event can reflect any kind of external factor that can impact the process as it progresses. And we have the connection. In the connection, we have the normal control flow between the task and the message flow. We also have gateway, logical gateway. And most importantly, we have the pool and lanes. So a pool, the whole rectangle, represents an organization, while the swim lanes inside it can represent specific roles within this organization. Of course, we can have different pools that work together, just like we will see later. We also have the artifact and the data object, which represents the data flow in the process. So just during our presentation, we'll have this example. And this is a simple example, just so we have a buyer, we have an authority, and we have a landowner. And these three participants are trying to interact together to move properties from one owner to another owner. So here we of course we abstract the process of the buyer and the landowner for the sake of simplicity, and we just focus on the authority. The authority starts with the first task. They register the zone, and then once they register the zone that the landowner can register the land in, they send a request to register their property or the land. If the zone is compliant with if the property is compliant with the zone, we proceed to register it. And then the buyer can just initiate a purchase request to purchase the land. And of course, the landowner can respond with the answer. So what we can see here is these interactions between the landowner and the buyer are happening through the authority. So the authority here represents a central point in the process as a whole. So this is the abstract deployment architecture of the process, and we can see how the authority is central, and they control the data and the keys. So So here, as I said, the participants don't own their keys, so thus they don't own the data too. So the authority can abuse this, or sometimes they can be single point of failure. So the other alternative is to get rid of the authority and just have the buyer and the landowner. However, in this case, as we can already see in the process, the areas marked as red, these can be faulty sometimes. So maybe since we have multiple buyers and multiple landowners, to have a single state of truth is not easy. So this is also how it could look like. Every participant have a fragmented fragment of the truth, of the entire truth. So we don't have a global view of the entire process state. Of course, we also lack governance. We don't know if we have a specific zone where we can register the land in, and nobody can decide that, since we don't have a central entity. However, the good thing about this is that the participants own their keys and also own their data. So what exactly we would like to have for our case scenario? We would like to achieve minimal user agency, which means that users own their keys and they sign their own transactions instead of relying on a central entity. Also, we would like to have some tamper-proof and also governed shared state between the participants. And the answer to this question is the next part of our work is the blockchain. So here the blockchain, we can see the data as central. However, this time the blockchain is not an external actor, or it's not a human or organization, but a piece of technology. So in this case, it might look as central, but physically it's decentralized. The data is replicated among all the nodes. And of course, the participants own their own keys. So we have a single state of truth. Now, how is this achieved? Of course, this is a different topic, but the blockchain, these are the basic building block of the blockchain. We have a distributed consensus, which means that participants need to agree on a single state of truth. Otherwise, the network won't function. And this happens, for example, through the proof of work consensus protocol. I'm sure many of you heard of. The second thing is the ledger replication. All the participants share the same ledger among them, which also means they share the same process model as we described before, and also the state of the process. And finally, cryptography, in this case, the keys. So PKI, and in this case, participants sign their own transaction, and we are able to verify their identity on the blockchain. So we can also achieve data integrity. So here, we'd like to talk about this important aspect of the blockchain. Anything that happens in the blockchain or via the blockchain is considered on-chain, while stuff that's happening outside are off-chain. Also, we have to say that to note that blockchain cannot directly interact with the external participants, but am I recording? No, I don't think I'm recording, but
Yes, you are.
okay. All right. So sorry about that. So the blockchain cannot directly interact with the external participants, but it is more of a reactive technology. It only reacts after something that has triggered it to react. And this happens through the event listener. So participants can only listen to what's happening on the blockchain and the blockchain cannot directly communicate with the participants. And so we usually refer to this as inbound and outbound oracles. So here, just to get a little bit off the topic here, but there was always been this trustless or confidence machine. So the trustless misconception, where we assume that the blockchain can actually resolve trust between participants. But blockchain as a technology, it just reflects the real world. So we can guarantee that we have an immutable transaction log, but that doesn't mean that the content of the transaction reflects what's happening in the real world. since it's coming from external actors and they can easily lie or manipulate the data, this transaction. So off-chain communication will always still be needed to resolve disputes. But the blockchain itself is a tool that can actually reinforce trust between participants. So in our work, we would like to assume that we have a low trust level between the participants. And yeah. So we have seen the two architecture and how they map to their business processes. But how does the blockchain architecture match to the business process? We can annotate the business process like this. We can use colors, we can use annotation, comments on the process itself, but that's visually not beautiful and not easy to the eye to catch. We can see. And also, we don't know exactly how to locate blockchain transaction in the business process. So here, for example, we don't know what exactly triggered this transaction, who exactly did it, and where does it start, where does it end, what does it include as execution logic. So we would like to have as requirements to be able to, the extension should be able to visibly separate on-chain and off-chain transactions, and also show us the transaction context in the process. So these are the elements that we suggest as an extension to the standard BPMN. We tried as much as possible to remain close to the standard language and not to invent some new constructs. So starting with the blockchain pool, and this is the main element in this extension. And here, what happens inside this pool is basically the blockchain logic or the blockchain data. Then we have receive and send transaction, and this is a task that represents transactions that are being sent from off-chain to on-chain. And we have the events. So when the blockchain emits an event, how do we catch it outside the blockchain? We also have the trigger revert event, and in the case of the blockchain transaction failing, how do we handle it from an off-chain perspective? And what happens within the blockchain pool, basically in the process flow? Finally, we have the block timer, and here we measure time through blocks, so not the normal time that we know. We will see the usability of this later in the examples. So starting with the blockchain pool, in the blockchain pool, we only can place the on-chain elements, of course, plus the script task from the standard language. And the off-chain part, we can place the off-chain elements, also the normal BPMN standard elements. So in this case, in this scenario, we can differentiate between on-chain and off-chain. And so the blockchain pool as a whole represents a network, just like the BPMN pool represents an organization. In this case, it represents a network, and the lanes in the pool represent a smart contract. Smart contract just on the blockchain has their own addresses too, just like external participants, and can be interacted with. So let's have an example in the send receive transaction. In this case, the authority registered their zone through the blockchain this time. And after registering their zone, they can off-chain communicate with the authority registered the zone, and then off-chain they communicate with the landowner, informing them that the zone was registered, and then they can register their land on-chain. In this case, the transactions are valid. The green boxes are validated on-chain and use the features of the blockchain, while the yellow elements are happening off-chain. It could be any type of communication. Moving on to the emit and catch events. In this case, after registering the property, we'd like to let the buyer know that the property is registered. So we use an blockchain event. And here we publish the event, and the whole network can listen to this event, of course, if they are listening. Once it is emitted, the buyer can listen, and then they can react. In this case, they send a request to purchase the land. And this is called an outbound oracle. And this is the trigger and the handle event. Here, for example, let's say that when the buyer was trying to purchase the land, it didn't work. So the land is not available. So what we would like to do is to revert the transaction. So, and this in the blockchain means that any states that had happened before the event is cancelled and rolled back to the previous state. Also, not only the data, but also the control for the entire process. So we're back to the point of purchase request. And the buyer is also informed by this, and they can compensate in a custom way off-chain. In this case, they just throw an error. They don't react on-chain. Finally, we have the blockchain block timer. And here the buyer, for example, waits 5 blocks before reacting. And this ensures that we have a higher immutability for the transaction to be included in the blockchain. As more blocks pass, we can guarantee immutability. So with these elements introduced, now we can actually discuss the semantics of these elements and how they can be executed. So we'll discuss the transaction, execution context, and also the deferred event execution. We'll talk about this. So to do that, we just like to quickly present the life cycle of a transaction within the context of a business process. So here we have the initialized state, and then we go to the ready state, and then the user submits transaction. We go to the pending state, and finally the transaction is completed. So to see this, when we place it in parallel with a normal standard sending transaction action. So the initialization phase, we deploy the contract when we initialize the task. So we assign the sender with the expected sender of the task, and then it's deployed. The external participants get the address of the smart contract so they can react with it. Secondly, when the receive task is enabled, which means the participant can actually now interact with it. They can send a transaction. So this is the submit phase here. The external participants send a transaction. And then we go into the pending. In this case, the transaction is being validated in the network. And of course, we wait until it's mined. Once it's mined, we complete the process, and the events are now visible to the external actors. So just to note here, during the execution, the external actor cannot listen to the blockchain event only after the transaction has been completed. And this is what differentiates the blockchain events than the normal standard BPMN events. In case the transaction was reverted, the external user can know about that, and they can send the transaction again, and then we go back to the ready state. This is just the execution semantics of this language. Now, something I didn't say during that explanation, that the transaction has different possible ways to conclude. And the first case, just like we've seen, was the end event or the revert event. The other case could be when the process flow meets another received transaction. In this case, the transaction ends and we wait for another transaction to be received. And also the last two gateways, because they're always followed by received transactions. So we expect the transaction to end there. So now what we can, answering the requirements in the beginning, we can actually see the transaction on the model. And here we can say that we have 3 transactions, possible transaction, the register zone, which ends after we meet the registered property. And now we have another transaction that ends until the purchase request. And the last transaction, the third transaction, is going to receive a purchase request. And that was at the end was the end events. We can also distinguish now between on-chain and off-chain, and we have separated them. So now that we have the on-chain logic contained into one place, we can actually compile this logic into smart contracts and then deploy it also to the blockchain. So that's also what we developed around this extension as a compiler. And this is just a snippet of code, Solidity code that we can get out of after we compile the process that we've seen. Just very quickly, Here, for example, is accessible what is called a modifier in the smart contract Solidity language. And here we, for example, we just make sure on the blockchain that the sender is the correct sender. We also check that the task is ready. And we also here, after we check that everything is okay, we execute the script and we also init the events. Finally, we change the state of the current process to complete it, so the next transaction now can be received. Here's just a simple, diagram of the compiler itself. We have the BPMN extension elements, which maps to, of course, we have the variables we didn't talk about in this presentation. And we also have the blockchain elements, which maps to the BPMN elements. And here, for example, we have the network, the smart contract, the external accounts, which represents the external actors, which are contained in the network. Yeah, just briefly this, and then, so now, since we have it compiled, we can deploy it, and what we can do after deployment, we can measure the cost. So the blockchain transactions are measured, are costly, they cost money to be executed. So what we would like to see is the cost of these transactions through our extension. So we have differentiated between two settings here with the one contract setting and two contract settings. So here we'd like to use the feature of the language to see how it impacts the cost. In the one contract setting, we don't do anything. The model is as is. In the two contracts, we separate the entire process into two contracts. So we have one contract for registration and one contract for purchasing or transferring the land. We deploy it, and then we know we can compare the price, the costs, and in the two contracts setting, we observe that this has a higher cost, and that's logical because we have duplicated logic that we need to use in two contracts. While in the first contract, the logic is the same for both logic. And in the execution cost, most of the transaction in both settings look the same, except the last transaction. And here we have the one contract is cheaper than the two contracts, and that's due to the cross-contract reference, because we have to call the first contract has to execute the logic of the second contract. And this is why we have a higher cost. And yeah, so now we've seen how we evaluated the language to the cost, and we also conducted a survey on the 30 users, and these are students in the BPMN class. So we assume that they have BPM background, and we asked them to transform centralized business process model into a blockchain using our extension. And we also evaluated the expressiveness and the usability of the tool. So this is before conducting the, that's how we had 40% of the respondent with zero blockchain experience. After conducting the learning outcome, we have at least 80% of these students has learned something about the blockchain. They didn't become expert, but at least they know something about the blockchain. And we also asked them to rate the expressiveness of each element, and this is what we get. On average, it's 3.08 over 4 for each element. The block timer wasn't included in the experiment. And also, we also conducted a usability study. Now we got a 60 or 0.42, which is acceptable for a start. And most of the feedback we got on this is on the tool itself, using usability rather than the language understanding. So as future work, what we would like to do is to include how the token, so of the cryptocurrency or the token flow within the processes. This is one of the most important aspects of the blockchain. We don't have it now, so we'd like to introduce more elements that can represent tokens of cryptocurrency. We also would like to support multi-instance process management. In this case, we only assume we have one instance of the process happening on the blockchain. And lastly, we would like to also see some strategies on the design side, on the compiler side, to achieve lower cost execution, which can be motivating for users to actually use it. And yeah, this is the conclusion.